All right, so yeah, how is it going? How can I help?
Okay, so I have sort of, I guess, three questions right now.
Mm-hmm.
So the first one is what, like the approach to non-dimensionalization. So
Uh,
yesterday,
mhm,
I made like a really severe error when I was doing question three, and it
mhm.
was the way that I defined data. So I incorrectly non-dimensionalized, and it caused the whole problem to be wrong, and I had to redo it. So I was just wondering,
Are
like
you, are you talking about for similarity variables, which was problem three, or in general about non-dimensionalization?
so I'm talking in general.
General. Okay, so in general, like non-dimensionalization, for a general problem, so a general problem, uh, typically, like I would say, you would do things like you will pick a length scale, such as L, and you will say x is equal to x by L, y tilde is equal to y by L, and so on. Okay, that's typically how you will usually do the coordinates. You non-dimensionalize the coordinates like this. Then for any sort of time, typically you take a diffusion coefficient. Now, if there are multiple components like dA, dB, dC, you can pick any of them. Let's say dA, and you can say tau is dAt by L square. Okay, and then once you do that, the third number typically that you will see in your particular, what we've been focusing on is damn Kohler number. And so that will depend on the exact reaction, and that can come directly from the equation itself once you plug in the other things. So for a first order reaction, this becomes for a first order reaction and so on, right? And so for a second order reaction, it would be KVCA L square by KVC naught L square by dA and so on. Obviously, there is also theta A is CA by C naught and so on. So typically, like what I would say is like you pick one length, you pick one diffusivity, and you pick one concentration, and you stick to it everywhere. Okay, like you stick to it everywhere for all the variables. Now, this is only going to convert an ODE into an ODE or a PDE into a PDE. So this is a general problem, which I think is, and if for the purpose of the exam, I don't believe there will be any question where we will not provide you how to non-dimensionalize. Okay, like we will ask you for a general problem. Okay, it will always be the case where you can figure out, like based on the information provided, like I have written down, that you will rearrange your equation and non-dimensionalize it. Now, a more specific question is what happens for similarity solutions? Because similarity solutions are slightly more specific. There, you're converting a PDE into an ODE, right? And so the goal is not just simply to make the equation dimensionless. The goal is to make it in a way that you can actually reduce from a 1D unsteady problem to a 1D problem, like from in terms of a variable. So that's slightly more involved that way. So for a similarity variable, I highly recommend thinking
just
about,
before we move on, can I ask a
yes,
quick thing?
yes, please do.
So, so when you were saying that, like for example, the theta A, you define it to be like CA over C naught.
Mhm,
So like in question three, that was a mistake that I made. I defined my theta to be like T over T
mhm,
infinity,
mhm,
but it turns out that it should have been like T minus T infinity, all of that over
mhm.
delta T.
Yeah, so I can explain why. So that what the way you non-dimensionalize it, you're still non-dimensionalizing it, but it's just not suitable for similarity solutions. And why is that? So for similarity variable, the first thing I would recommend for you to understand is how do we what's the point of similarity solution? So similarity solution is always trying to find a master curve. So you have things changing in space and time, and then you're trying to find a master curve, right? So essentially now, if you look at the problem homework 2, problem 3, particularly, so there, because we had initially t of x comma 0 was t infinity, right? So the profile was like this, right? and then we started adding flux at the x is equal to 0 location. So the first profile would have some temperature raised here. It will go like this. Then I will have more temperature raised here because my boundary condition is that the slope is constant, or minus k del t by del x is constant. So I am essentially going like this, something like this, profiles will look like this, right? So now these are my profile in time for x and time temperature. Now the goal is to find a theta of eta that can collapse to, right? So that's the goal. Now, if you just scale t by t infinity, right, and eta by x by delta, you will rescale and so you said, well, I understand this. Wrote this as x by delta, and when I chose delta as square root of alpha t. But if you still simply scale t by t infinity, these points will still be time dependent, right? Because you're just dividing them by a constant number. That's it. So you're not trying to kind of then trying to find a master curve. So I mean, like, you are non-dimensionalizing your equation, but you are not non-dimensionalizing your equation suitable for a similarity variable, which is a more specific task. So non-dimensionalization can be done arbitrarily, like the way I have done on top for a general problem. Okay. But for similarity solutions, your goal is to find a master curve. And in that case, what you're trying to do is you're trying to capture this time dependence of the x-axis by saying, well, it is stretching more and more out. So that's why I am trying to, like, scale it back by delta, because delta is increasing with time. So this point is slowly going further and further and further away from my x-axis. So then I'm trying to scale it back and kind of collapse. But then that's also happening in the y-axis right now. And so that's why you had to scale it differently. And that's why you had to write t is equal to t minus t infinity and ts minus t infinity, which you then had to estimate as from the boundary condition as q naught delta by k, right? And now you can see that what you're doing is delta is increasing with time. So your y-axis is now being squished over time, which makes sense because temperature delta T is increasing with time. So you're squishing it so that, kind of stay in the same zone. And then the same thing you do for the x-axis, you're squishing it with time. So that's the idea. So similarity variables non-dimensionalization is one step further because you have to find a master curve. It's not just about, getting a non-dimensional number. Make sense?
So in general, it's a good idea to consider the change in the profiles, the temperature profile, the concentration profile before we
Depending on
start
the
to.
problem. So in this case, clearly the temperature is changing. But what if I say that temperature was fixed at T wall, right? So if I
Mhm.
know my temperature is fixed at T wall, and I'm just saying they are going further and further away like this, then you don't need to do that, because in that case, it's simply, you can just say T wall by T infinity, you will be fine.
I see. So in that case, on the y-axis, there's no need to scale because it's
Correct.
all
Correct.
okay.
Yeah, so like that's
That makes
exactly right.
sense.
Yeah, so it's, I mean, you can still say, I mean, it wouldn't matter. You can, I mean, if I'm in your position, I might still say T minus T infinity by T wall minus T infinity, just because I would want to make it go from 0 to 1. However, this is right, but you can also say T by T infinity, and this will be fine as well. Because we can see we are scaling, it will just go from 1 to some number, right? That's all. But those both will work because these are constant numbers. You'll just add some constant values. But here the problem is if you do this by theta st by t infinity, then this is not going to work because it's clearly time dependent. So I've
Yeah,
not basically found a master curve.
yeah, that makes sense.
Yeah. Yeah. Maybe let me ask Tatiana for her question, and
Yes, I
then
was
we
gonna
can, yeah, and then we
pass
can,
it
yeah,
over.
okay, yeah, perfect. Hi, yeah, please feel free to ask question, Tatiana. Yeah.
Hello, I was working through the practice exam
Mm-hmm.
again, and I got to problem 3, and I think I
Mm-hmm.
just need a little bit of clarification
Mm-hmm.
when it comes to um so when we're this is like the wall question that we did in class, and I have written down that for like heat transfer boundary conditions Q,
Mm-hmm. Mm-hmm.
um like the Qn equals H with the T minus the T infinity.
Mm-hmm.
And we talked about how n like points towards the ambient. And I
Correct.
think I just need a little bit like further clarification
Sure.
on what that looks like.
Yeah, absolutely. Yeah. So this was problem 3. And so we have this block, and then we have so the question is for y is equal to the, yeah, so we have h is equal to, not this way. This is t wall here, and then we have h comma t naught, h comma t naught, h comma t naught. Then we have y is equal to w. This is y is equal to 0, right? Then we have x is equal to 0 and x is equal to L. Okay. So now, so what you have to focus on first is, let's, like you were just saying, we will first find the normals pointing into the ambient. Okay. And so this is the normal pointing into the ambient. This is the normal pointing into the ambient. This is the normal pointing into the ambient. Now, the only tricky thing is, which, I mean, it's not tricky, but you just have to be careful here, is that our coordinate system is y pointing downwards. So this becomes EY, this becomes EX, and this becomes minus EX, right? Does it make sense?
Yes, that does.
Okay, okay, perfect. And then now my condition is Q dot N is equal to H T minus T naught, right? H T minus T naught. And so with that in mind, let's do it on the left hand side with this in mind. And Q is always minus K del T per del X EX plus del T per del Y EY plus del T per del Z EZ. And so that's Q always, right? And then my on the left hand side, I'll multiply this with dot EX, and I'll get is equal to H into del T minus T naught. I mean, I'm just showing you the full process just to clarify, and then obviously this does not come into picture. Or sorry, this is minus EX, not plus EX, my bad. Minus EX. So you get K del T by del X at X is equal to 0 is equal to H T minus T naught. Okay. So that's the first point, right? Makes sense. And on the right hand, boundary here, this boundary here, it'll be the same thing, but with a negative sign remaining, because my normal is not minus EX, it's plus EX. So it's
Yeah.
a minus K, yeah, minus K del T by del X. So, and then for the bottom, the Y is equal to W, I also have a plus EY, so it'll be minus K del T by del Y is equal to H. So, yeah, so in this case, I will have A as the correct answer, and then A, D, and F. Yeah, makes sense. Yeah.
Okay, yeah, that makes sense. I think I was getting harped up on like only doing one, but I see why you have to do all three. Okay, perfect.
Yeah. Okay,
Cool,
correct.
thank you.
Yeah. Any other questions from your side?
Not right now, but I might
Sure.
stay and
Yeah, please feel free to stay, and this will be recorded, and so you can stay here and just mute and turn off the camera, whatever you want. So I'm here.
Perfect.
Okay,
Yeah.
yeah, you can unmute anytime. Yeah, Joan, you can go ahead with your other questions. Yes.
Okay, excuse me. My next question was sort of to do with boundary conditions.
Mhm.
So specifically like question 4 in the homework. So
Uh,
it was the boundary condition at r equals to 0, which was
yes.
there's no
Mm-hmm.
there's no rate of change at r equals 0.
Mm-hmm. Mm-hmm.
So it's not immediately intuitive to me, like why that's the case. Like so for example, like if there were some rate angular dependence, for example, like it makes sense that at theta equals 0, it's the same when theta is 2 pi. Like something like that makes intuitive sense, but the the one where at r equals 0, there's no change in r. It doesn't make a lot of physical sense to me. So if you could give
Yeah, for
us
sure.
some intuition, would
Yeah,
be
yeah, for sure.
helpful.
Y at R is equal to 0, del T by del R is equal to 0. This was homework 2, problem 4. And so the first thing is you kind of already said that. So right now our theta, we are axisymmetric system, right? So our system is axisymmetric. And so in the sense that there is no variation with theta, right? So if I was thinking about creating a control volume, I hope you would agree that you would say my control volumes would look like sort of these small slices of cylinders, um, something like that, right? So like it'll be in the DZ direction and then some sort of rings like that, right? Now, with that in mind, does it make sense that if you have any flux, if you have anything going in, it also has to come out on the other side. At R is equal to 0, there is no reason, there is no way for it to have any sort of flux going in. If there is a flux going in, it also has to come out, right? So that's the physical interpretation. The mathematical interpretation is that all of these systems have a 1 by r del by del r del t by del r kind of Laplacian. And if you have r going to 0, your del t by del r has to go to 0 because otherwise you'll get a blow up of your solutions. So if you actually do mathematically, you will start to see the general solution for Laplace is C1 log of r. And so you have to have that sort of derivative go to 0, otherwise you'll have a mathematical blow up. Physically, I just cannot send anything at this. It's just like a bit, because so in a Cartesian system, you always get these nice, strips or like a square or like some sort of like nice geometry. But in a cylinder, you're getting these shells, right? So the shells are decreasing in sort of this, in this area. So I'm essentially going to a point, and I'm going to a point as I go, like, going to a point when I'm thinking of r is equal to 0, and I cannot have any derivatives there. If I have derivatives, the solution would be discount, like would be, maybe this is another way for you to think about. So if I am thinking about a profile of t versus r, right? T versus r, right? And then if my profile here doesn't have a derivative equal to 0, and if I sketch a profile like this, right? Right? If I sketch a profile like this, you can imagine when I convert it back to x and y coordinate system of beyond the origin, I will get some sort of a non-smooth line. So that's also not physical because I'm kind of generating heat or consuming heat at that point. So because it's a point, it has to have a well-behaved system. I cannot create heat or so that's sort of the other way to think about it. So is essentially a lot of people. I mean, this question is, by the way, this question has been asked like over and over again, and a lot of people have different interpretations. So one is the mathematical interpretation that solution blows up. The second is the physical interpretation that you cannot really have something going in. The third, which was kind of related to the second one, is that you will get like it's a symmetry condition in a way that you're symmetric about r is equal to 0. And because you cannot have otherwise you are you're having some finite flux. When will it break down, let's say? So maybe that might help you. So if I a somehow I have a very a way to create, like at the center of the cylinder, I have a way to create a surface heat, or like some thin line that I can push it inside the cylinder that is emanating heat, then I may be able to break that down. Yeah, so like that's the one interpretation, but otherwise it'll always apply.
So I wanted to add something to that. Like the mathematical rationale is to do with like boundedness, right?
Sorry?
The mathematical interpretation is to do with boundedness. Because if we allow for r to 0, the solution will go in an unbounded manner, and it would blow up, as you said.
Yeah, you can say
Yeah.
finiteness. Yeah, that's
So
fair. Yeah.
okay, so the thing about, okay, at least in the PDE's class that I'm taking, how we deal with Laplacian, the Laplace's equation on a circular domain, a steady state, is that we solve out for the general equation, and it will look something like constant plus some log of r plus like r to the power or something plus r to the power of like lambda, I think.
Mm-hmm.
Yeah, so what we do is if r equals 0 is in the domain, that means we're on a circle, not like an annulus.
Mm-hmm.
Then we would simply just say, oh, because log is unbounded at r equals
Mm-hmm.
0,
Mm-hmm.
and r to the positive lambda is unbounded at, or is it r to the negative? There are two terms that are negative. We simply just say that the coefficients must be 0.
Yeah, and so I think that's a fair interpretation, but at the same time, now if you do that and take the derivative of your solution, you will find with that boundedness approach that your derivative is 0. So it's the same, it comes out to be the same. So like what you're saying is exactly this identical to saying derivative is 0. Because what you're saying is, well, my solution is bounded, which I fully agree with. And so you will have that coefficient, you will drop out that coefficient
Yep.
with the law, because like you said, you cannot have a solution otherwise. And so what I'm saying is if you take the derivatives at r is equal to 0, r to the power lambda terms will go away. The only thing you will be left at is c1 by r. And that's why you can say that with the same logic, you can also convince yourself that the derivative is 0. So it's the same thing. So if it helps you, you can also say, and by the way, some people do say that. Like what I'm saying is, I'll, probably the most common argument is the symmetry argument. But there are people who would say because of the boundedness of the solution, we'll just drop off this term or write the derivative to be 0 or what. So those are all equivalent interpretations of the same feature.
So after we drop the logs and one or the other term,
Mm-hmm.
we're saying that if we take that derivative
Mm-hmm.
and evaluate it at r equals to 0, then like I guess like I'm struggling to make that connection to the derivative
Yes.
being
So what I'm
0.
saying is that if you drop that term, if you make it bounded, the derivative would automatically go to 0. Like there is no, like you will never have in your solution r to the power of 1. You will always have a solution r to the power of lambda or higher, whatever lambda you had. So it'll automatically, if you bound your solution, which you did, then you can, one step further, you can try to evaluate the derivative of a general solution at r is equal to 0 without that log term, and it will always come out to be 0.
Okay, at lambda equals to 0, that one I completely agree because we'll be left with a constant term, right?
Yeah.
And when we take the derivative of that, then it'll be 0. So that makes
Yes.
complete sense.
Yeah.
But in the lambda equals 1 or greater,
One
there's
is
still
not one is not a feasible solution.
as in for a lambda.
Yeah,
I mean like,
lambda is equal to 1 is not a feasible, like r to the power lambda is equal to 1 is not a feasible solution for your Laplace equation.
oh no, what I was referring to is like, so okay, we're talking purely about the radial component, right?
Yeah.
So the radial component in its most general form
Mhm.
takes the form of constant plus log of r plus some polynomial like r to the power of positive lambda plus r to the power of negative lambda, if I recall. That's like the radial solution.
So yeah, I mean, sure, but I think it's not sure it could be that, and but I don't think lambdas are free to choose, is what I'm saying.
I think the lambdas will be dependent on the the other bit, like the one that has the homogeneous boundary conditions, right? And then we'll find that the lambdas are some kind of
Yeah,
like n pi or something.
yeah, you can find the solutions, that's fine, but I don't think you'll ever get r to the power of, what I'm trying to say is like you just cannot have it, like if once you bound it, you
Mhm.
cannot have a finite derivative. You can convince yourself, like you don't have to trust me. You can
Okay.
try to convince yourself, it's just not possible. Like you will not, so what you're saying is you can see the argument. So just give me 1 second. Yeah, just give me 1 second. I'll be back. Sorry, yeah. Yeah, so yeah, you can try to convince yourself about like this form, but you just cannot have that structurally that equation will not appear. So I think even the book has the general, if you're trying to do with the FFT approach for the cylindrical coordinate, with RZ, the book also has the solution actually. Let me see if you want to take a look at the book's solution. Um,
Do you have the page number? I have the book.
yeah, the book would have it for, look at page 169.
69.
Yeah, and then look at 3 and 4 kind of forms of the solution, and 169, and then I
Yep.
think they might even have
It's like a table, 5.3
yeah, table of what kind
table.
of structure of solution would look like. And then I think you might want to look at problems. I mean, 5.7-2 or 5, I think 5.7-1 is a good one
Okay.
because that has a problem, kind of a heated wire and stuff like that. So
Okay.
yeah, yeah, take a look. Yeah, so look at 5.7-20, which is page 187,
Yep.
and look at that sort of the form you will get constant plus some sort of a 1 minus r square. That's your steady
Yep.
state solution. And then some
Mhm.
time dependent solution will come out, which again, that for us is, but you never have an r. Like what I'm trying to say is like it's an r square. So that's why the derivative at r is equal to 0 will go to 0. And then it is just the structure of the equation will not allow it.
I see. Yeah.
Uh,
Okay. That makes
and uh,
sense.
and in fact, cylindrical geometry is a tricky one. Like, but nonetheless, so yeah, so that's the
Okay.
main point. Yeah,
So I guess that implies that there's a constant, like it's constant at r equals 0, right? Like
yeah, yeah.
the
Constant is
dependent
fine.
variable. It's the
Yeah,
same as the derivative of 0.
correct. Yeah,
Okay.
yeah.
Okay. I'll hand it over to Tatiana if she wants to ask anything.
Um,
I do have a question.
sure. Yeah.
Um, I think you guys might have been talking about it like right before I joined. Can we just like go through the similarity
Mm-hmm.
solution part
Mm-hmm.
of it again?
Mm-hmm.
I'm trying to I think that's the most challenging part for me of how to choose your theta and your n and stuff.
Okay. So how about this? So what I would suggest is let me try to do the problem which we have not done, so that you see one more example of that, and it's in the supplementary video, and this is just so that you get a practice, and then we'll come back to the same homework to problem 3. Okay, so I think we can do that. So let's see here. So what the problem in the homework, that think of it like this. It's simply like if you drop, let's say, 1 gram of some solute in a liquid, right? And you drop it at x is equal to 0. So initially all the mass is concentrated at basically this location, x is equal to 0, x is equal to 0. And because it's 1 gram and there is no volume, volume here, I mean, the right approach is this is not a 3D system. We're just thinking of it as 1D. So I'm dropping some, let's say, 1 milligram per meter square or some sort of an aerial mass at that point. And so if I'm just dropping, the concentration is practically infinity at that point, right? At t equal to 0, it's an infinite concentration. Then I'll slowly diffuse out something, and it will kind of go like, the solution will look like this because I'll go down. So, and then slowly I will have some sort of a curve like this, and I will have a curve like this, and so on. Okay, so this is sort of the problem. So the main constraint here is that Cx of time dx from minus infinity to plus infinity is some sort of a constant m. Okay. Now, so this is because it's basically saying that when I integrate out all the concentration, it will always sum to some mass, capital M. That's sort of the main part. So I'm dropping it. It's just that the distribution is evolving over time and space, but I will always sum the overall concentration will always sum to capital M. Okay, that's the idea. So Now, the problem in this, the challenge in this problem is that now I want to find a master curve, right? So again, I can say my governing equation. So the first step is governing equation, del C by del T. And I will not explain the full thing, but I hope that makes sense that simply diffusion, there is no reaction, there is no convection, and so we get this. The second thing is I know that the concentrations far away are going to die out. So you will just have the boundary condition would be that um, CA of x comma 0 is in a way everywhere 0, all right, at time t equal to 0, except at that at exactly x is equal to 0. Everywhere the concentration is 0 at the initial condition, right? I'm just dropping it at that x is equal to 0 location, except when x is not equal to 0. And then we know for infinity comma time, um, this is equal to 0, and del CA by del x. So it's essentially saying this is some symmetry. There is because I also have minus infinity, so we can just solve this half and then just flip it and do like a symmetry condition. So this is kind of our system in a way. This is sort of the equation system. And now if I want to relax and again create a master curve. So whenever you're thinking about um, a similarity solution, I always encourage you to think about a master curve. How would a master curve look like before you even like think about the suggestion, right? So if how would a master curve look like? So how would a master curve look like? So now in this problem, I hope it makes sense that my concentration at at x is equal to 0 is dropping over time, right? It's going down and down and down and down. Whereas my spread on the x-axis is increasing over time, right? So technically, I would compress the x-axis and stretch the y-axis because I want to find a master curve, right? So in a way, I am saying I'll compress the x-axis and stretch the y-axis with time. Right? So I hope that makes sense. So this is key because basically we are kind of going further and further and further, and then we're going here we are kind of trying to stretch out because it's decreasing, so I'm trying to stretch it out. Here it's increasing, so I'm trying to compress it. That's how I'll find a master curve. Otherwise, there is no other way for me to find a master curve. Now, with that in mind, essentially, the thing to consider here is I don't have so you can do the scaling analysis and you can say some CA you can do I mean the scaling analysis. I hope that's easy. Scaling will say delta x is some delta, and then you can convince yourself that delta will scale as square root of DAT. This has always been true for all problems except that diffusion might change to alpha, but that's essentially this, it goes as square root of time. Now the problem here is I don't have a concentration. I just have a mass. I don't have a concentration, right? So the way to look at it is basically I need to find a concentration from this number, right? Because this is where I can just do the best estimate my concentration. So what I'm saying is I want to find theta of eta. In eta, I can see my delta is doing the job because I can write x by square root of DAT. With time, I'm compressing my x-axis because as time is increasing, I'm bringing it smaller and smaller, like I'm stretching, collapsing everything. That makes sense. Now for theta, I need a concentration. Obviously, I will have some sort of a concentration, theta. Theta is equal to Ca by something at the denominator, but the denominator has to essentially decrease with time so that I can, stretch it out. Like the denominator of the eta was increasing with time, this has to decrease with time, right? So what the proposition here is that we can assume, this is just like this is an approximation again, is that I can try to think of it like this: the concentrations profile can be thought of approximately like sorry, like this, like that you approximate to some level of this concentration, Cm, constant over the delta, and then zero everywhere else. With that in mind, you can say this number would look like some Cm delta is equal to m, because a dx is simply just a length, like becomes a length when you integrate out, and some concentration Cm, which is the maximum concentration, and then that total mass is m. So with that in mind, the Cm becomes m by delta, and I get this as the theta. Okay. So now you can see my delta is increasing with time, so I'm stretching out the axis, right? And it is decreasing with time, so I'm compressing the x-axis. So with this substitution, if you go back and do the problem, it turns out that you will get an equation. It becomes actually comes out to be the Gaussian, looks like a Gaussian spread, right? Gaussian spread. So it becomes that, and you can solve it and so on. So that's not something we are going to do, but this is an example where both x and y are changing with time. Okay. Now let's go back to this problem now. Okay. So in this problem, what we're doing is we are pushing the flux at x is equal to 0, right? And so initially the temperature was this. I'll sketch it now with the red color. Temperature was this at x is equal to 0 was this T infinity. Then I'll slowly start to increase the temperature at x is equal to 0 because that's where I'm putting the heat in. And then over time, this will increase because I'm continuously pushing in the heat, right? If I'm continuously pushing in the heat, the temperature has to rise because that's where I'm pushing in the heat. Because, or in another way, you can think of it like this. My boundary condition is minus k del T by del x is equal to Q. And so temperature is dependent on my delta x. So you can think of it this. Right? So TS is, and that's where you can see the delta is increasing with time again. So clearly my TS is increasing with time, right? So now when I want to collapse the y-axis, I again cannot simply say T by T infinity, because if I say T by T infinity, I'm not compressing it. Now I have to compress the y-axis as well as the x-axis, because this is becoming higher and higher and higher with time. This is also stretching out higher and higher in time with the x-axis. So I have to compress both of them. Otherwise, I'll not get a master curve. And so with that, you can I hope it makes sense that we're looking for something like d minus t infinity and ts minus t infinity, because this number clearly is increasing with time, and then t minus t infinity is constant. So I can essentially over time, so this is what you did in your homework. Make sense?
Yes, I think so. I think I'm gonna rework this problem and then do the one on the practice exam because I think this is kind of the weirdest concept for me to
Sure,
try
for
to
sure.
think about.
Yeah. Please, and by the way, I should note that the idea and similarity variables is always going to be tricky. It's a little bit of an art. There is no like exact way to do it. But I would say these three cases, when it's constant, I hope it makes sense. Your y-axis is just fixed. So you don't have to, like if the temperature is fixed here, you simply just scale by T wall, or T minus T infinity by T wall minus T infinity. Both will work. Doesn't matter. You will get the same answer eventually. But it's when the things are changing with time in the y-axis that you have to kind of be careful. And this, the third one, these are the three classic. They are not like, there is no other actually typical set of similarity solutions. Then they become much more specialized, which are beyond the scope of this course. But like these are the three cases that you have to think about. And again, I encourage you to, it's just my way of thinking about it, that it's a master curve, which we are trying to find. So that's why I'm scaling the y-axis and x-axis this way. But also read the book if you kind of, it's confusing book, might help out kind of, with thinking about it. Yeah. Any questions, Tatiana or Juan? Any other questions?
I think I'm good. I'm good. So thanks for the review.
For sure, yeah. Let me know. I'll be here for another 30 minutes. You can log in anytime or mute yourself. Feel free to ask questions anytime.
Okay, I have to head out, so thanks.
Sure.
See you. Have a good
See
day.
you. Yeah.
Hello, Encore.
Yeah, hi.
Can we walk through? I'm not sure if it like affects the problem all too much, but
Hmm.
for perturbation,
Mhm,
when we talked about like the example we did in class, we did a second order reaction, and
mhm,
now I'm seeing like first order
mhm,
reactions.
mhm,
Like I understand what that means in like concentration and stuff like that, but does that
mhm,
affect the problem all that much?
mhm.
Um,
Yeah, for sure. Yeah. So how about we do the nth order reaction? So
okay.
that might make it a bit clearer for you. So this is the problem. Um, yeah, this is the problem in the just trying to look through the this is the part two problem practice exam problem 5,
Yes.
right? Yeah, okay.
Yeah.
All right, so this is practice exam P5. So I'm just letting you see so what's the small Damkohler number is the Damkohler number, and then it's the first order reaction. Um, mhm. Okay, yeah, okay, got it. Um, yeah, so yeah, I was thinking if nth order might be too difficult, but we can try. So so it's not the end of the word. So let's do that. So I will just do for the sake of it nth order right now, and then we'll figure it out. Um, so this is the basic, setup, and then as it kind of, and this is steady state, steady state. So we do get like, d square Ca by dx square is equal to kV Ca raised to the power of n now, which is the nth order, right? And then if you do the non-dimensionalization, we'll say x tilde is x by L. Um, then the Damkohler number will define as kV Ca to the power of C naught to the power of n minus 1. This is just you can verify this is just it becomes very easy once you do the. So for the first, sorry, there is also a dA missing here. So dA. So this is the Damkohler number that you will get out, and you can verify this. It's not too bad, and you will get d square theta by dx square is equal to Damkohler numbers times theta to the power of n, right? So this is our equation non-dimensionalization, and then theta of 0 is 1, and theta of 1 is equal to 0. Uh, does this setup make sense? So it's the same thing that is in the exam, except now n is just arbitrary. So we can do second order, whatever we want, right?
Yes. Yeah.
Now, so this is the small number epsilon for us now because this has been given to us to be small. So we will now take and say substitute theta as theta naught plus epsilon theta 1 plus epsilon theta 2 square. So let's do it this way. I mean, as I have said in the class, you will not get anything beyond first order correction. So maybe let's just stick to that because it can take long. I mean, you can always expand more, but let's just stick to this, okay? Now, always remember, we also do it for the boundary conditions. It's not just the expansion. So in the governing equation, this becomes d square theta naught plus epsilon theta 1. Don't know why I'm writing it as phi again and again. Is theta 1 by dx tilde square is equal to epsilon theta naught plus epsilon theta 1 to the power of n, right? And here you will get theta naught plus epsilon theta 1 of 0. Here also you'll get theta naught plus epsilon theta 1 at, x tilde equal to 0 is equal to 1, and then theta on theta 1 0. I've just plugged in the value for all of them. So now we'll collect orders now. Epsilon 0, epsilon 1, and so on. So for epsilon 0, we can see on the left hand side, we have d squared theta naught by d tilde square, right? That's our first order. But on the right hand side, I have everything multiplied with epsilon. So I really cannot have anything. So it will be 0. So this is identical to the exam, right? Similarly, we'll also not do the boundary condition. As you can see in the boundary condition, on the left hand side, I have theta naught, the epsilon to the 0 power, but I also have 1 on the right hand side, which does not have any epsilon coefficient. So I will say it becomes theta naught minus theta naught of 0 is 1, and similarly theta naught of 1 is simply 0, right? Okay. Now I will have similarly I can do the epsilon to the power 1. On the left hand side, I clearly have d square theta 1 with d tilde square. Now for the other one, which is the epsilon theta naught to the power of n, I need to know, I need to expand this whole thing. Like if it's a square, then, but we can see whatever except theta naught to the power of n, which is going to, so if you remember the binomial expansion, it's theta naught to the power of n, and so on. So, but the first term would be theta naught to the power n, but everything else will have an epsilon in it because like it's the second term. So the only coefficient that remains is then theta naught to the power of n here. Okay. So that's here the order is coming in. So the order matters in the first order, in the first correction. This is agnostic to my nth order, which also makes sense because if I don't, this is no reactions. So it's always the leading order solution is easy. You just turn off the reaction, right? And if you turn off the reaction, it doesn't matter which order it is, right? It doesn't matter which, but now it would matter which order it is if I go to the second one, which is clearly the order. So now, I mean, if you solve this, takes a little bit of time. This is theta naught is 1 minus x tilde, which is a linear solution. And so this will become 1 minus x tilde to the power of n. And then we have to kind of integrate this whole thing out for a general n. Don't do that, but just to show you the example that now it would matter which order I have and so on. So so the order does matter, but not for the leading order solution, for the theta ones. So when I write back my full concentration, when I say theta is equal to theta naught plus epsilon theta 1, this term is constant, but this one is going to be dependent on the n. Does it make sense?
Yes, yeah, I understand that.
Yeah. Yeah, and so I wouldn't like you will not get like any kind of this nth order calculation. I would say I don't remember did we give also 1 hour 40 minutes for the last year's practice? 1 hour 30 minutes. Wow. So the exam that you have is definitely much shorter than the one, and this was definitely one of the longer exams that I've said. So your exam is not even like this particular problem. I did feel it was a bit rough for students just because it had so much math. So you will not have that kind of math for sure in the exam that we have set.
Yeah, I think that's kind of where I ended up, like even in the homework, finding your
Yeah.
thetas is kind of where I would get lost just because of
Yeah.
how heavy in math it is. But
Yeah, there will be some math, but it won't be this
yes,
much. Like
yeah.
I think this problem I debated. I remember last year. This was actually not even last year. This was a spring semester this year. So
Okay.
I remember I was like, oh, maybe this is, but sometimes I run out of problems, and so like I also have to create new problems every time, which are trying to test, new ideas and like thoughts, and so
Yeah.
sometimes you're just out of creativity. So I thought it was a bit of a lazy problem because it had just a little bit of maths test, but I mean there will be something on perturbation, but not this tense is what I'm trying to say.
Okay. Perfect. Yeah. Makes sense.
All right. Anything else on your mind?
I don't think so. I feel like I'm in an okay spot right now.
Okay,
So.
perfect. Yeah, let me know if you have more questions. And yeah, I'm surprised there was basically only 2 students. But you can always email us and we'll reply. And then yeah, we'll see you tomorrow for the exam.
Perfect.
Okay,
Thank you so
perfect.
much. Have a
Yeah,
great day.
yeah, you too. Bye bye.
Bye.